Right, so I start recording once again. And yeah, Jeff, the floor is yours. Welcome, welcome to the second keynote speech.
So we're going to kind of come down back to earth a little bit after Tony's talk. My talk is somewhat more pedestrian and mechanical, let's say. So spikes for cognition, hyperdimensional computing with spiking phasers. So I'll describe all that stuff. I'm from the University of Waterloo, and this is describing some work that I did, started when I was at Western Sydney University on sabbatical last year. So first of all, there was a request for ideas for a hashtag. So I had an idea. Also, there was some talk yesterday about rebranding, and I find it a little bit uncomfortable, the fact that there's VSA, and it's not even really agreed upon what VSA stands for, vector symbolic architecture or algebra. I can be convinced either way, and this hyperdimensional computing. So maybe we need a new term, and you can take it or leave it. I thought structured vector encoding is kind of a nice compact thing. And so I mean that seriously, but sort of a joke is structured vector encoding networks is Sven. So this is kind of a Swedish name, I think, right? So before I get on to the content of my talk, this is the route that my daughter Adelaide and I drove from. It took us about 4 days or so, and we went to the Lofoten Islands, and it was absolutely spectacular. So we took pictures like this and like that, and I guess last thing I want to say that's sort of off topic is that one of my bucket list items, which I came up with a bucket list, I don't know, 5-10 years ago. One of the items was to be in the Arctic Circle near one of the solstices. And so this has been a dream come true for me. In fact, with the VSA Online stuff, I found out that Evgeny was like near the Arctic Circle. So I was starting to scheme ways to invite myself here before this thing came up. And I was like, this is absolutely perfect. So thanks for organizing this. And it's a dream come true. Okay, now back to my day job. Vector symbolic architectures. So this is my slide to motivate vector symbolic architectures. You're all motivated. Okay, let's move on. Yeah, I thought Tony was supposed to give a tutorial on FHRR before me. I thought that's why you put him before me, but I guess that never did happen. So I'm going to talk about this flavor, Fourier holographic reduced representation. And you're probably mostly familiar with this. We have these operators, similarity and bundling and binding and unbinding. And in Fourier HRR, these vectors A and B are these complex vectors, but they're unit modulus. So the only thing each number is really encoding is a phase, right? And similarity is basically this complex inner product. Vector addition. This is what I'm using for Hadamard product. So element-wise multiply. And I'll show pictures of that shortly. And unbinding and permutation. Okay, so this is kind of just making sure we're all on the same page. And this is the canonical example, which I'll refer to a little bit later. So I've got this vector here, Q, which represents a red square and a blue circle, and I can query it and saying, tell me about the square. And I get sort of cancellation here. And so I get red plus noise. So now specific to FHRR is when A and B are these complex unit modulus vectors, or what we call unitary vectors. They look like this. So A is a vector like this, and phi 1, phi 2, phi, all these phi's are different phases. B are different phases, thetas. So the binding of those two vectors is the element-wise multiplication of them. So you get this. and it was with complex numbers. It's really nice because it's really just adding the phases, as it turns out. Okay, so that lends itself, and this is something Paxton, I saw in Paxton and Alpha Renner's paper recently, like, yeah, adding these things, you can sort of turn this into spike timing. So I'll get to that in a second. So why spiking? Why spend this time taking something that's easily implementable as a bunch of complex vectors and bash my head against the wall trying to figure out how to turn these things into spikes? And it's because when I was in Sydney, and they were doing these I was in the International Center for Neuromorphic Systems, and they create these FPGAs which run these neural networks. And it seems, I think it's in general, neuromorphic hardware works best, and you get sort of like the best energy performance on spiking networks, spiking substrates. So that's why. Now, the details of comparing my spiking phasor algorithm to just a complex vectors and all that stuff, that's kind of up in the air because it really depends on what particular neuromorphic platform you choose. And I haven't yet done the full analysis of this sort of stuff yet. So that's work to be done. Okay, but hopefully there's a home for the spiking things in the future. Okay, so let me talk about spiking phasor networks. What the hell are those? So here's something I ripped off right out of Paxton and Fritz's paper. So this just shows a bunch of spikes from a network that's just cycling. So this is a 5 Hertz network, and you can see that in this 0.2 seconds, every neuron spikes once, and the next 0.2 seconds over, they fire with exactly the same temporal pattern. Now, the timing of each spike, you can represent as a phase within the cycle. So this green one's kind of just a bit past halfway, and this light blue one is kind of at the beginning of the cycle. So this phase angle and the spike timing are basically isomorphic to each other. So there's phase angle, and there's the element of the complex vectors. So spike timing, phase angle can go back and forth between them. So now it comes down to how do you add phases? Because I showed you that binding is basically adding the phases, right? So when we have two neurons both projecting to this green neuron, we want, this one's spiking at a particular phase in the cycle. This one's spiking at a different phase in the cycle. We want this green one to then spike at a phase that's the sum of these two phases. Okay, therefore doing the phase summing. And so in the picture, I'm looking for this sum of the phases. So this is a time axis now here. So we've got phi 1 is the one phase, phi 2 is the other phase, and we want to add those together. It's for when the green neuron spikes. Okay. So Paxton and Alpha had in their paper described a neuron model with integrators and some. I read it and read it and read it, and I didn't really understand. It's too brief. I don't know how they did it, but I thought I could do that. I'll do my own. So I started making my own neuron model that would add phases, and then I got carried away, and then I made like other models that do all like the other operations. So that's where all this stuff came from. So let me describe to you what neuron model will add the phases of the incoming spikes based on this work. Okay, so incoming spike here and here, and I want the green neuron to fire at the sum of the phases. So first of all, we have an integrator, a built-in integrator. It's just counting time. It's just a timer. It counts up until the first spike arrives, and then it stops counting up, levels off, and then once the second spike arrives, it starts counting down. So it's like embarrassingly simple. And that's where the green neuron fires. So it's actually just slightly more complicated than that. I'll explain why in a second. We actually use two integrators. one that does the counting up. You can see now there's this faint blue one here. Once the first spike, it gets the first spike, they swap. And then the blue one levels off, and then the blue one counts down, and then we get our spike. And here's why we do that. Because if the sum of the phases reaches into the next cycle, it's a pain in the butt, and you have to now start counting up with the red one before the blue one's done counting down. So that's why you need to separate the two different integrators. Okay. So this is kind of a theme among these methods where you need kind of two integrators to sort of account for the fact that your computation could actually reach into the next cycle. And then there's one more. Now this is annoying. There's one more integrator built into each neuron. So now each neuron has basically, most neurons have three integrators, just linear integrators built in. And this one's just the cycle tracking. And its job is just like all these neurons are cycling at the same frequency. We need something inside the neuron to know when the cycle starts and when the cycle ends, because we're talking about absolute time within a cycle, right? So each spike has to be taken in context of a particular phase in some global baseline cycle. So it'd be nice when I get time to sort of come up with a better mechanism. I contacted Paxson about this work, and I said, hey, I've been doing this. I know you're doing some of this. Like, I want to make sure I'm not just doing everything you're doing, but one paper behind. And he said, no, that's pretty cool. And then the one thing he asked me, he's like, how do your neurons keep track of the cycle? And I said, well, this. He's like, yeah, okay. He was disappointed because he thought maybe I had something smarter. But I think it's basically what he's doing too. Maybe we'll come up with something better. Maybe you've got a better idea. Who knows? So I implemented the stuff in Brian too. So if you've seen Brian before, it kind of looks like this. These are basically differential equations. Like the rate of change of X, P, and Q, they're basically integrating. And then it's beyond that, it's just like details. And then when different events happen, there are these reset equations. Okay, so I've shown you this neuron model that can add the phases of the incoming spikes. What about subtracting? Because we have to do unbinding. Actually, I can't remember who spoke, but maybe it was you, Ross, that no, I don't think it was. Anyway, this idea of unbinding, but instead of calling it unbinding, let's just reverse.
Yeah, yeah.
That was you. Yeah. So I kind of like that better. So anyway, but here's for better or for worse, here is a subtracting phase model. So subtracting phases, we're interested in the time between the two spikes. One spike arrives, second spike arrives, and the interval is what we're trying to measure. So first spike arrives, we count, and we have a timer that counts up to the next one. That sets a threshold. Oh, it's really hard to see. There's a very faint line there. It's a threshold that is set, another variable inside the neuron. And in the next cycle, this other integrator counts up to that threshold and then spikes. Okay, very similar story to what I was saying before. And if that's all done properly, then that spacing there matches the spacing of this neuron firing. Okay, so now we can bind vectors, unbind vectors. And these vectors are stored just in a population of spiking neurons. And they're all going at the same frequency, but the timing of their spikes in the cycle is the vector, is the hypervector. And you can have two populations projecting to a third population. And if it's binding them, it does this phase, does a spike addition thing. Now this third population is encoding the bound, those two bound vectors in FHRR. So last sort of little neuron model I want to show you is that multiplying the phase of a spiking neuron. So in FHRR, you can do this fractional power encoding, or at what in Waterloo we like to call fractional binding. So here's a complex, unitary complex vector, and we can bind it with itself, right? And then we can get, basically, we're just doubling the phase, right? So the nice thing about FHRR is you don't have to just double it. You can raise it to some power alpha. And so this new vector here, complex unitary vector, is encoding alpha, essentially. and it doesn't have to be an integer. So that's fractional power encoding. And then you can do things like, so I've got this x to the negative 2.14, that's fractional power encoding of negative 2.14. And if I compare if I take its similarity with a bunch of other vectors, you can see it peaks at x equals negative 2.14. So this, I mean, many of you have seen this sort of stuff before. I'm just sort of reiterating. In Waterloo, we call these spatial semantic pointers. At least that's what Chris Elias-Smith has gone with. Although they usually do stuff with HR, and they do Fourier transforms kind of on the fly in layers of connection weights. This is a bit different because we're actually encoding the complex phases. So we're already in the frequency domain. Okay, so just to summarize what I've done so far, I've got a neuron model that does convolution by adding the phases. I've got a neuron model that does deconvolution by subtracting the phases. And I didn't really talk about the sort of innards, but it's a similar kind of story to do the phase multiplication. It's an integrator, and then when the spike arrives, it sets some threshold, that sort of thing. Okay. I also have a cleanup memory. It's like a spiking hop field network. It's kind of based on the similar work, like by a lot of stuff by Paxson I've read. This is also motivated by the modern hop field networks by Krotov and Hopfield. So we have here's some. So you can imagine we have hypervectors of dimension 3 because I don't want to draw more than 3 circles. But this is some pattern, and I want this pattern. Maybe it's got some noise in it, right? Just red plus noise, but I want it to converge to one of the vectors in my vocabulary. And so cleanup memory is what I'm after here. And so I don't think I need to spend too much on this because I think you're all pretty familiar. So I can project it to this layer, which is kind of a one-hot representation of the different vectors in my vocabulary. And then if I project it, these are resonating fire, so they're inhibiting each other. So they kind of converge to a one-hot solution of what's the best pattern that's coming in. So you sort of set this up with something close to one of the vectors, and this kind of goes back and forth, and then it converges quite nicely to one of the patterns. And so, yeah, so you give it red plus noise and it converges to red. Okay. So here's just a pictorial demonstration of that. So here's the input, and it's 64. It's a hypervector of dimension 64, and I've sort of zeroed out half of them. So only half of the neurons are actually firing. And in addition, these are actually kind of noisy. They're sort of temporal noise is added to it, or phase noise. And this top part is the population is projecting to. This is the Hopfield population. And you can see after a while, it sort of starts to fill in the pattern. And in addition, well, you really can't see this, but there are like really light gray dots there. It shows that it's even fixing the sort of phase noise that was here and converging to the actual pattern that was one of the targets. So it works. That's my point. It works. So it looks interesting, but does it do anything? So I've got these neuron models. Now I could build these neural networks in Brian too, spiking neuron networks. And I can do these sort of vector symbolic architecture kind of things. So just a few toy examples of it working. Excuse me. So here's a finite state transition machine. Very simple. It's a stopwatch. There's like 3 different states: cleared, ticking, and paused. And in each state, there are 2 different buttons you can press. So they're basically 5 vectors that represent the different states and actions in this model. And so you can do things like, okay, let's say we're cleared in the cleared state and we press start button. It should go into ticking mode. Ticking state. So as a vector, you can say, so we have 5 vectors, C, T, and P, S, and R. So you combine C for cleared with start, press the start button, and we want to go into the ticking state. So that's a vector, hypervector, and you can query it with something like that. You can say, what happens when what happens if I'm in the cleared state and I click start? Where do I go based on this transition? So you sort of fill in and do the algebra, and things cancel, and basically it also works. Goes into the ticking state. So this encodes a single state transition. I'm in some state, I take some action, and I end up in this other state. So I actually have in this system, I have 6 different state transitions. With in each state, I have 2 different things I can do, right? So there's 6 different ones, and I can just bundle them all into a single vector. And so now this single vector encodes all the state transitions, and I can query it. So just a simple little network, I encode that into a population of a bunch of spiking phases. They're just neurons that are cyclically firing, but their phases have meaning. And I can have a couple other populations, one that the state I want to query and the action I want to query. Bind those using my little phase summing population. And unbind them again with my other neuron model. So this population should, in theory, be encoding that. Then I put it into, this is just a technical thing, put it into my help field network, and it should converge to one of my vocabulary vectors. So this entire network has 706 neurons. Because I think I chose the hypervectors are only 100-dimensional, 100 neurons, spiking neurons. So this is just you have to trust me. This is just a printout of the results. They all the output, this is a similarity. So it's got the correct answer, and the similarity was 0.99965, whatever. The worst in this case was 0.93 similarity. So it's fairly robust. I haven't really pressure tested it and seen how many different state transitions. There's just a toy model. So future work. Spatial memory. So here I'm saying 480 neurons. What I mean by that is the populations that encode these vectors are 480 neurons. So these are hypervectors of dimension 480. So I can do things like I can say there's a red square at coordinates -1.3, -1.1. So that's down here. And I can bundle that with blue circle at a different place and a green triangle at different places. So all this goes into this vector M, this entire sort of spatial configuration. And I can do things like I can say what's at location -1.3, -1.1. And this shows the similarity with all the different vocabulary vectors, including ones that aren't even really part of the situation. Like there is no green circle, but I threw it in there anyway. It's compositionally plausible. And you can do things like show me where either the blue circle or the green triangle are. And it'll give you a heat map like this. So this is the same sort of thing where we take a grid of XY coordinates, we produce the corresponding hypervector and compute the similarity with this vector here. And so you can see it's most similar to these 2 places. So in that sense, it encodes the locations of those 2 objects. So this is work done by Nicole, who I don't know if she's given a USA Online talk. Yeah. All right. So, but wait, there's more. So that basically is stuff that I wrote up and got that accepted to Icons, which is in Santa Fe in August. So I'll be going there. But then since then, I've sort of beefed it up even more. So let me talk a little bit about function bundles. So here's a function of x, f of x, and it's just like that. So you can encode a sample of that function right here by saying, okay, the x is 0.14, let's say. So I can, if I have a spatial semantic pointer or some hypervector x, I can encode 0.14 in that. So now that's a hypervector. I can take the y value, if you like, also and encode that as another hypervector. So I have two different hypervectors, one encoding the x coordinate, one encoding the y coordinate, and bundle those together. I'm sorry, bind those together. So that represents a single sample. And I can just do that for a whole bunch of samples and bundle those all together. So now this vector m represents that entire sampling, that entire function. So this is work by Mike Furlong, who I think some of you know, and I think maybe he also gave a, oh, I think Nicole and Mike gave a joint talk, yeah. Right, okay. And so Mike has, so I ran this past him like, hey, what do you think? He's like, he had some ideas. He's like, why don't you try this? So these are actually trajectories, if you like, through this two-dimensional space. And so he's done work with representing trajectories in a 2D space with a bunch of samples. And so what I'm showing here is a bunch of samples along this function added together, just like I showed you. And if you, again, compare them to, you compute the similarity with all the other hypervectors you can generate from these different locations, you get this sort of heat map, and you can see the heat map sort of fairly well follows the function itself. So in addition, Mike said, well, he has these Gaussian processes. I don't know if that's right, Gaussian process. So it's a function, but the function, it's really gives you, there are two functions. One gives you the mean, one gives you the standard deviation. And so for any x value, you have a distribution, you can sample that distribution. So you can see things widen out here and they tighten up and they widen here again. So this is showing, I don't know, about 3,000 samples of this Gaussian process. These hypervectors are of dimension 8,640. That comes from basically how many x samples I needed and how many y samples I needed. I don't think that's correct. Anyway, if I'm pressed on it, I'll justify that better, but okay. So this technique sort of naively can encode these distributions as well. I know it's a bit patchy, but Mike's using this to represent distributions and other functions and trajectories and interesting stuff like that. Integrators. So an integrator is a computational element that takes some derivative as input and then computes the integral of it, or computes the function that derivative came from. And so, for example, you could input velocity, and what you want is your integrator to output the position as a function of time. So I thought, how can I implement an integrator using spiking phasors? So imagine you have a neuron that's spiking at some phase. So here's the beginning of the phase, the end of the phase, and this neuron happens to spike at this phase. And so you can see its integrator inside, it's got this integrator counts up, oh, threshold, boom. And it just keeps doing that ad infinitum if it's just left alone. But then it's got some input. It's got spikes coming in right here. So this is a bit after the beginning of the cycle. So that's saying just increment the phase by this much. So in that sense, it's going to integrate that incoming spike delay. And so I implemented another one of these simple little neuron models where you basically take the time that this arrived and you can decrement this variable p by that amount. There's another gray line that you can't really see, but you can see that this will delay this red spike by the timing of that green spike. So it's the same idea as adding the phases, but same flavor. And then if it's a bit early, it's going to cause this spike to happen a bit earlier. So I could basically take this stream of input spikes that are centered here on this sort of zero, but it integrates their sort of deviation from that phase start cycle starting. And so these are the input spikes. These are encoding the velocity. So this is 200 neurons encoding velocity. It's a spatial semantic pointer. This is integrating all those little spike deviations from zero. And what's interesting is, even though, you know, there's this thing with the phases, that if you keep adding phases together, you get this wraparound, right? Which can be a problem. If you want to take a phase and multiply by 10, it's like keeps going around and you land on some other phase somewhere. Now you take that phase and say divide by 10, it's right, it's already removed all the laps it's done. And if you say divide by 10, it only looks at the phase modulo 2 and divides that by 10. So multiplying and dividing in the phase I did isn't really invertible, because it kind of moves, it's always modulo 2 pi. So, but with this thing, with this integrator, you're always just adding increments that are way smaller than 2 pi. So it can build up stuff that cause lapping, phase wrapping, but you can undo all those too, and it'll sort of keep all that accounted for properly. Excuse me. So anyway, just a quick demonstration. The blue is the derivative and the red is the ideal integral, and you can see the dots that my network spits out. Follow that. So using the integrators, kind of taking them to the next level, Legendre delay network. Now, I don't know how many people know what a Legendre delay network is. A few of you. So it's basically, I have a picture. So you get some input signal, F. So this could be some time, like continuous domain time signal, and it's feeding into this network. This network is recurrently connected, and its job is to, you can decode from that network different delayed versions of the input signal. So you can specify a delta. I want a 0.27 second delay, and you can decode a signal that's 0.27 seconds delayed. Or you can decode functions of that delayed signal. Or you can decode, yeah, that's right, any function of that. So I wanted to see if I could get my network to do this. And this is, so these Legendre delay networks, you basically have you're using the Legendre basis. So you're basically integrating these coefficients. So in this case, I'm integrating 6 Legendre coefficients. Each one is just 20 phasor neurons. So this shows the entire population is 120 neurons. And you can see that over time, these solid lines are the true Legendre coefficients that I would get if I was just doing a really accurate integration. And these dots show that my spiking phasor integrators. One thing is that to do this integration, I have to increase the frequency. So a lot of the stuff I showed you before is like 5 hertz, like these phasors are running at 5 hertz or 10 hertz. Once you get to the integration, if your frequency is too low, too much happens between cycles, and you can't capture all the little wiggles, right? So I think this is a 40 hertz cycle. And so 120 neurons. And this shows a bunch of decodings at different delays, all encoded in those 120 spiking neurons, all that. So in summary, spiking phasor neurons can implement vector symbolic architecture operations, or should I say, spiking phasor neurons can implement structured vector encoding operations. So I just showed you a bunch of kind of gave you a flavor of the neuron models. And these spiking phasers can implement VSA networks or SVENs using a relatively small number of neurons. I guess that was one of the sort of ideas is that so Chris Eliasmith and his group, and they have Nango and the neural engineering framework, they can do all this, but it takes like 1 or 2 orders of magnitude more neurons. So they can write a neural network, create a neural network that will do everything I just showed you. But where I use 700 neurons, they might use, I don't know, 10,000 neurons or something. So this is because a lot of what they do is basically rate coding. He would kill me if I said this in public, because he doesn't like to, there's more to the neural engineering framework and Nango than rate coding. There's more to it than rate coding. There's nothing explicitly rate coding-esque about neural engineering framework. But I'd like to add this stuff into it because this is explicitly time coding. It's not even close to rate coding. In fact, I've got some ideas of creating populations that do rate coding and spiking phaser encoding simultaneously. Okay, and I showed a few examples, this state transition, the spatial memory. I didn't show that picture, but I showed you a 2D version of that. Integrators, function bundles, Legendre delay networks. So next steps. So it'd be nice to make it run faster. Brian 2 is okay, but it has this kind of annoying compile phase where you say, go, and it sits there for about 60 seconds. And then suddenly it runs the network. So I don't know what it's doing. So, I mean, of course, Mike and I have been working with the Intel group. And so, you know, it seems like we should maybe run this on the wiki. But when I wrote a proposal for this stuff saying, hey, INRC, why don't you fund this project that he didn't fund it? So now I'm searching for other, I'm kind of mad at them. So I'm going to see if I can implement it somewhere else. The first thing we're going to do is put it in Nango, I guess, because we're right there. Robustness tests. So I haven't stress tested this. I haven't played around much with what happens if there's a bit of timing error in the spikes. What happens if we're missing spikes? This needs to be sort of a need to push the system to try those things. Here's something I'm really interested in, SSP cleanup decoding. So this is fractional power encoding. We have cleanup memories for discrete vectors. And that seems to be a solved problem. Cleanup memory for these sort of fractional power encoding spatial semantic pointers is kind of trickier because there's no, there's a spectrum, right? So, but there's I have some ideas for how we can basically constrain those vectors into at least a unitary complex vector, because they'll drift away and they'll not even be unitary vectors anymore. So that doesn't make sense. Why are we doing that? We should at least try to bring it back into unitary vectors. And so we're trying to figure out, maybe grid cells are this sort of coupling mechanism. I don't know if you probably know what grid cells are, but there are neurons in your brain that basically, as you're walking around through a room, they fire at specific locations and they're arranged in a hexagonal grid. It's quite amazing. If you haven't heard of grid cells, you should look into it because it's astounding that a part of your brain basically lays out a grid. So your neurons will have a grid in this room. You go into that room, you'll have a different grid. You come back in here, they'll rearrange the grid to the same grid that you had when you were here before. So somehow it's your brain's recognition of this space. And it lays out this grid. Nobody really knows why. It seems like these grid cells, Nicole has been doing some work that shows, and my other postdocs doing some work that show the grid cells are actually, when we use these spatial semantic pointers in reinforcement learning tasks, it seems to learn things faster. It just seems to be a better representation for state for RL tasks. Anyway, some work there. Yeah, can we come up with something smarter than every neuron having its own timer? I mean, obviously that's a problem. As soon as I start introducing noise, all the neurons sort of internal timers are going to get out of sync, and then nothing will work. In fact, I think I tried this and it completely fell apart. So shh. And finally, I guess an analysis of information efficiency, or kind of like a runtime analysis of like, okay, what is this better? Is it faster? How many multiplications does it take? Because these things are running at like, they're basically doing time integration, right? These Brian 2 models are time integrating, and they're going at, this time steps are 0.1 milliseconds, so 10,000 steps per second. That's a lot of computation, but I'm just saying like, yeah, but if you put it on a neuromorphic platform, that's all for free. So I think I need to kind of put it, do a little bit of thinking there, justify that a bit better. So this is my team. You saw Mike and Nicole, but I have other talented students. Many of you know Terry, I think. So I work pretty closely with him. He's sort of responsible for me getting these postdocs. They're partially funded by NRC. Well, entirely funded by NRC. And yeah, thank you very much. Thank you.
Yeah. I have a small question. Maybe you have answered it already. Most likely you did. I mean, on your last slide about semantic pointers and grid cells, but so this is the case of really superimposing vectors, right? So when you start to deviate from unitary amplitude.
Yes.
So basically, yeah. But at the same time, you had this examples of kind of combining several items together. So how did you solve this problem?
Okay, so the bundling, I do have a neuron model that does bundling, but only 2 vectors at a time. But a lot of these things, like the example I showed was 6 vectors.
Yeah.
So that's all done in the, you're not supposed to ask, that's all done in the complex domain. We bundle it. This is, Frady does this too, so it's okay. So we put it all together because once you bundle something and you have to normalize it back to unitary, and that's a problem, right? Because you lose information.
Exactly.
So typically, what we do so far is you add it all in the complex vector space.
And then you include.
Then after all that, then you normalize it, make it unitary.
Oh, okay. Yeah.
I played a little bit with like the order that you combine. If you're just adding two together at a time, I played with obviously the order that you add them has a profound impact. So I've tinkered with that, but haven't really found something worth publishing.
Okay.
Oh, sorry, Dennis, you had.
Go ahead, Dennis. Okay. Well, first of all, awesome talk. I have a bunch of questions to ask you offline. But 40 gigahertz is super fast. So do you have I assume this was simulation, but do you have a target technology? 40
gigahertz?
Sorry.
40 hertz?
Oh, did you say 40 hertz?
These are the high frequencies were at 40 hertz.
Okay, never mind.
Yeah.
Question retracted. But I'm still curious whether you had a target technology or this is just pure simulation at this point.
It is simulation. But like I said, they're FPGA I'm just not a hardware person. So I don't quite know how to start to actually try putting it on a hardware like a neuromorphic platform. Mike, we are working with the Intel people. So in theory, they have Loihi 2 to implement things on. In practice, it's all in software.
Yeah.
So yeah,
okay.
A non-answer.
Now I have a lot more to talk to you offline about.
Okay, good.
Very cool. Thank you.
Yeah, because the stuff you're doing is like super high speed and yeah.
Very similar.
Yeah. Okay.
That'd be cool.
Interesting.
Yeah, I guess my question was sort of connected to what Pat was asking about hardware in the sense of I was just curious because I never worked with Brian, but are there any maybe compilers that you just deploy on hardware? Like I think.
Yes.
Is it somehow
there is some
getting are there any bridges there?
I think it's called. There is a GPU wrapper around Brian. I tried to install it. before and had issues. I've since replaced my laptop with a newer one, but I haven't yet had the time to try. And I guess since I'm thinking of just moving on to a different platform, I should really do it in Nango because that's sort of the lingua franca of the University of Waterloo. So that would sort of integrate my work better with them. But yeah, there's a GPU version of Brian too. Mhm. Mhm.
Yeah.
Oh, sorry.
Yeah. You decide. So we take it on a kind of conflict resolution manner, condition resolution.
Okay, I already pointed.
I was wondering if you thought about like making the patterns like really sparse. But then I just thought about now, if you said you have a problem with like you do your fun things. And I was thinking like if your patterns were super sparse, I guess you could just impose them, just forget about the they would then I guess be very neural. They both want the pattern.
Yeah.
About the activation. You could just they say in the brain, right? You have this set plus or minus 2 anyway that you can infer.
So here's so how do you, given that these neurons are all cycling at the same frequency, what does it mean for a neuron? What does it mean to be sparse if they're all cycling? Like what phase should we choose for a neuron that's not active?
Doesn't right business.
Yeah. So I have played with that a bit where I basically added a bit of code to, if a neuron's, it'll like turn off. Yeah, I haven't played a lot with that, but it caused some problems and you start binding things together, they get less and less sparse, but maybe cleanup memory would fix that. Yeah. I think with the SSPs, it becomes awkward because when you're trying to multiply, it requires more thinking, but that's the direction it could see going.
Yeah, actually, I was just continuing on from that when you were talking about the binding and effectively you could, depending on the values of the arguments, you're pushing the spike into the next cycle. And I would interpret that as being sparsity of that neuron within that cycle, because there's no firing within that cycle. So effectively, you've no longer got every single element being a unitary phasor. You've got some with magnitude 0.
But that's transient.
Yeah. But
after that, then it's
no, absolutely. But it was something. My question was going to be about what are the implications of that? Is that really sparsity, etc. But okay, so that's you've covered that. Next question then was you've got so binding, and this is sort of more fundamental mathematical question. I mean this seriously. It's not a gag question. You've got the two basic operators in VSA are effectively there's some kind of a sum operator, there's some kind of a product operator. And you think, oh yeah, I know what addition is, I know what multiplication is. But multiplication is at least partially isomorphic to addition because you can do multiplication by adding logs, you're doing multiplication of phases of complex numbers by adding phases. What's the essential mathematical difference between multiplication and addition? And sort of how is that reflected in the operators?
That's an interesting, I see your point where multiplication is actually just repeated addition in arithmetic.
Yeah, but in this, it's not even repeated. It's just I'm adding two phases, and yet it's a multiplication somehow.
Yeah, I guess it is. It's essentially a log space. It's multiplying in log space is addition.
Yeah, I mean, and relating that back to the previous point about sparsity and so on, I wonder whether if you're looking algebraically, in addition, you've only got one special value, which is 0. Whereas in multiplication, you've got effectively two special values. You've got 0 and 1. So 1's you know what value, and 0 is a lose information value. So if that's the difference, mathematical difference between addition and multiplication, then the existence of 0 would seem to indicate that it's fundamentally related to sparsity because you're losing information. I don't know anything about maths, so that's really sort of a question to people who do.
Yeah, there is a singularity.
I thought it was have simply operations. Of operators which have certain properties, so they define certain mathematical structures in terms of combination. So it's not difficult to reverse commutativity and distributivity. It literally doesn't matter what the operations, only the combination of properties matters, and whether more than one operation interact with each other. Back to what I was saying, VSA is tough and things don't matter, and the others fight with each other.
Yeah, so quick, I have one question about your slides, but a quick response to Ross there. I think that's an really interesting question. What's the difference between the multiplication and addition operations? And one of the answers I would have to that is that in VSA operations, the addition preserves similarity and the multiplication operation destroys similarity. So that's one big difference between. But going back to your slides, I love the way you were using the spatial encoding. Could you flip to that slide? You had the spatial memory. So I think that was the first slide that you had on it. Yeah, that one. Yeah, and here what you're showing is you're encoding the spatial location in an absolute frame of reference. And I was wondering, could you use the same tricks to encode relative?
Yeah, it all comes for free. I mean, so this is the stuff that Nicole's been doing in addition to others. But yeah, she does like path integration. In fact, it's really nice. Even the path integration. Yeah, it all works. Like you can do the integration in FHRR with these vectors. So yeah, you can say how far, like what's the relative position of this to this, and it'll give you the vector, the SSP representation.
You could like pose a question like what's above the blue circle.
Yeah, and she does stuff like here's a region. What's in that region? And it'll say this and this and. Yeah, or it'll show a similarity to both green triangle and blue circle. Yeah, it's and she's also got things like edges, representations of edges and corners, and she's really sort of probing into the whole hippocampal representations like place cells and edge cells and wall cells and stuff like that.
That representation almost seems like you could use any arbitrary like spatial location vector to define your frame of reference. For example, like the problem, like what is above the blue circle? Like it wouldn't have to be, would it have to be like an event there, or could it just be like some arbitrary location that you then like
you could
find with your query?
Yeah, it's compositional in nature. So yeah, you can query it with whatever sort of spatial or object oriented query you like. Yeah, Dennis, you've been patient. Okay, well, you first.
And we have one online question.
I was very quick, just a very quick question.
Hi, Jeff.
Wait, just a second, Vidura, just a second. We have two questions here in the audience, and then you.
Quick comment on like funding versus funding, things like that. So it turns out that in certain settings, if we work with entity-based encoding, we can demonstrate actually that addition of abundant operation in the original data domain corresponds to concatenation. So there is a formal way to demonstrate that. While the binding operation corresponds to the TensorFlow. So these are basically the two different from in terms of like if we have two tuples and like if we encode them into hypervectors, so if we perform binding on their corresponding hypervectors, this corresponds to TensorFlow is a regional domain. If we do bounding, then it's concatenation in the region. But that's as simple as that. You know. Subject to fixed encoding. Once we start changing encoding, it might be different. But yeah, if we just use it in the style of random projection, if we just randomly project data in 5-dimensional space, then this is what happens.
Chris?
So curious to chat more about grid cells online or offline. I did like a neuroscience master's, and so I'm really interested in that topic. But regarding the implementation of like the spiking and the binding operation, I was curious about what the like implementation would be or look like if you like in a neural system, spikes might arrive or might not arrive. And so you might not know a priori how many unbindings or bindings you have to do. So it seems like I was just wondering if in that kind of case where you need to perform a flexible amount of bindings, would that just amount to adding more integrators and solving the problem, or just extending the integrator to count the number of spikes you thought about? Yeah.
I think the way this is imagined currently is you have a network of populations. Each population is performing some function. So you might have two populations that are basically just spitting out vectors, like they're basically spiking to represent two different vectors. They'll both project to another population, and its job is to bind these two together. And so you can kind of have this, this graph of populations, and each population is performing one of these operations. So a binding population only receives projections from two populations. So each neuron should only get 2 spikes per cycle.
Oh, okay. That's the way you would do it.
Yeah.
So if there's like 4 bindings or something, you do like a kind of tree structure of.
Yes. Yeah.
All right, we turn to online question. Vidura, please.
Hi, Jeff. So I'm working with Dasin and Evgeny on a similar approach. So we have been working on basically rate encoding. Can you hear me?
Yes.
Yep.
Am I audible? All right. So Jeff, I read your paper as well. So I have one technical question. So in your paper, there's this global cycle which basically synchronizes all the neurons. So what happens if, so basically what we are doing is you are encoding the phases to time.
Mm-hmm.
So what happens if these, the summation of these times exceed the global cycle, or is there a way to tackle that? Or
Yeah, that situation's quite
what's the approach?
In fact, one of the slides I showed addresses that specific thing. So you're saying I'm adding 2 phases, and if those phases add up to something longer than the cycle, then the spike should occur in the next cycle, right? And so that's why, is that the question you're asking?
Yes, Jeff. Yeah.
Yeah, that's why we have 2 integrators
Yes.
to sort of handle that, because if there's only one integrator, then then that's a problem, because it basically you have to start timing the arrival of the first spike. You have to start that at the beginning of the cycle, right? But at the same time, you need an integrator to count down to when the spike should happen. And so if that count down and count up, they can't happen with the same integrator at the same time. So that's why we have 2 integrators. One basically counts up until the arrival of the first spike. The next one counts down from that level from the arrival of the second spike. So between those 2, Mike Furlong and I were talking about, repeatedly we were convinced we had a solution with a single integrator, and then every time we like, oh no, that's whatever, things break. So I'm currently convinced we need 2 integrators to do that. And I think Frady and Alpha Renner, their model essentially has 2 integrators, or at least 2 compartments in their neuron. Thanks for your
All
question.
right, Jeff. I have another question. Jeff.
Okay.
So on Brian too, so all of these are like done on simulation, right? Like
Yes.
is
Yep.
there any way to like port them to Loihi or something like that?
Yes, I mean, there is, Mike and I are talking about, Mike put a proposal into the Intel neuromorphic research, neuromorphic research group community. They want to do VSA stuff. So I think he wants to sort of port some of this to Loihi. As I said in my talk, I'm considering other alternatives. But Nango, I know Nango's not a neuromorphic platform, but it's a language that does sort of make some of those available. Yeah, those are, and also GPU, I guess. I could come up with a more GPU friendly implementation. So yeah, so far I just developed this in Brian 2 and have not yet attempted to accelerate it.
All right, any questions?
Good, Jeff.
Yeah, sure. Okay, go on.
Legendre delay network question.
Yep.
Okay, so if I've understood it correctly, you encode the input signal, which is a function of time, scalar function of time, into a hypervector. Is that right? Which is the Legendre representation of it. And then you decode from that some function of the delayed input signal. So you've got a separation between the construction of the representation, which then as a separate step allows the extraction of some function of the delayed input signal. Is that right?
I think I understand what you're saying. So I think the input values are represented using a spatial semantic pointer.
Okay, yeah. So it's effectively a hypervector representation.
Yeah.
Right. And then that readout of some function of a delayed version of the input signal, what's the functional form of that? Is that effectively just a linear projection or something a regression to do it?
What I demonstrated here, basically the stuff I've shown here, it's almost disappointing because the results I get with these spiking phasors are pretty much identical to what I would get if I just did everything in the complex vectors. So so basically I was representing the Legendre delay network, the coefficients in these spiking phasor populations.
Okay.
And then basically, once I've encoded it, I just pull out the phases, convert them to complex vectors, and then I do the reconstruction of the Legendre polynomial from that.
Yeah, because what I was really wondering about was that the readout process. So if it was something like just a linear projection, then the stock standard way to do it would be vector matrix multiplication. You learn the weights offline or whatever, or construct them. But I was wondering whether, if that readout process, you've got the shape of the function and you've got the time delay, I was wondering whether you could actually parameterize that readout process in such a way that you could specify the desired time delay with a hypervector. So that would then allow the possibility of having a process where the desired delay of the readout could be some dynamic value that was created elsewhere in the circuit.
First of all, the entire readout can be done. I'm convinced can be done using spiking phasors. Yeah, because as the question was asked, you can add these spatial semantic pointers in the hypervector space. Can you choose the time delay? Yes, the time delay is basically just maybe it's just a dividing by a scalar. So as long as you can divide by a scalar, you can get a different delay. So it's a linear operation in that sense. Well, linear, yeah. I think so. I'll have to think about it more.
I suggest on this positive note we wrap up and thank we're on our streaming in Zoom in about 1 hour, 10 minutes.